VSWR and matching confuses a lot of people. To be blunt with you, even as a lecturer, I knew exactly how to work things out, but I didn't really in my stomach understand what VSWR and matching is all about. Now, imagine that you're sitting in a car. That's my best analogy, and it is exactly the same thing. You start driving the car. Car's got a 70 kilowatt engine. It can pull away. But what you must do then, put it in fourth gear while it's still going at 20 kilometers an hour. And you'll suddenly find this thing doesn't want to accelerate. That is a mismatch. Okay, that is exactly a mismatch. In other words, in a car or any engine needs to have the right torque and the right RPM. So for your typical engine, go watch where it's maximum power, perhaps at 3,500 RPM. And at that point, it will have a certain torque, and there it will deliver its 70 kilowatt. The car, on the other hand, needs, when it's slow, it needs a lot of torque, not much speed, okay? And that is like resistance is equal to the ratio of voltage over current, and the car needs the right speed over torque, okay? The engine needs it, the car needs something different. So your gearbox is a variable matching network. And you can see here that when you're at a very high speed, by the way, with the car, you put back to second gear, that same 60 kilowatt engine will slow the car down and its revs will scream, no power output. So it is the transfer of power. In other words, you struggle to transfer, or if there's a mismatch, you cannot transfer the power of this engine to the wheels. On an antenna side, if you've got a badly mismatched antenna here, you will not be able to transfer its power to the receiver, the same when you're transmitting. So, seems hell of a serious. And after explaining to you, and I hope you really understand what's going on here, it's not efficiency, okay? It is just that the power doesn't want, we call it reflected, but the power doesn't want to go in, okay? Because it's not got for receiver, we want V divided by I to be equal to 50 ohms, okay? And of course, no antenna gives you like a nice resistor, but we want it close enough. Now, second problem. Years ago, people made a sort of golden rule because radios were more powerful, and they said VSWR must be lower, less than 2 to 1. Now, 2 to 1 VSWR, how much of the power is lost when you've got a VSWR of 2 to 1? Hey, people, only about 0.5 dB. Okay, very little if you think about it. At 3 to 1, I think it's roughly 1 dB. And then if it climbs up, reading 5 to 1, you're losing a lot. You could look it up, but 5 to 1, my quick guess is you may be losing 3 dB. That's a lot, okay? But in the beginning, the reason why the people stuck to this 2 to 1 belief is it wasn't a belief. The output resistors or transistors of the radio, if it's a 2 to 1, needed to handle twice the voltage, twice the current, either one of the two. And that type of voltage and current made you had to use an expensive transistor. So you want to use the cheapest, and restricting this allowed you to use transistors, otherwise they burn out. Later on, people just pull the power down. But our modern stuff, okay, our cellular and Wi-Fi, doesn't give a damn. Okay, they can even operate into an open circuit. They use much lower power. Transistors is no longer the issue, but people still stick to this. What I'm trying to say to you after this very nice, hopefully understandable explanation in terms of VSWR is you can often, for well-designed antennas, you can often just ignore it. So go look at this spec sheet, make sure the VSWR doesn't shoot above this. But the fact that it goes over 3 to 1, you know, if you design an antenna from 600 to 6 gigahertz, that happens. That's not going to cause you that much harm. So leave the obsession. It's like spec sheet problems again. So people now design antennas to be lower than 2.5, and it's just because spec sheets seem to always say you have to do it. It is pretty irrelevant.